All right, good morning, everyone. Welcome back. We're going to jump back to the high-level runtime today. Hope you all enjoyed Sean's first level presentation the last time. So if you'll remember, the last couple of times we've been talking about the operational pipeline that exists inside the high-level runtime. And today we're going to take a brief diversion from that, although we're going to see a piece of the pipeline that we were sort of ignoring before, and that is we're going to actually look at some of the hardware resource managers that the high-level runtime provides as part of its internal services for doing different operations. And one of the ones that we're going to look at is going to be the processor manager, which we've seen very briefly as part of the pipeline. But we're going to actually look at it in a little bit more detail today. Before I jump into the processor manager, we're actually going to look at two of the other managers first, which are a little simpler. We're going to look at the message managers and the memory managers. So let's dive right in. So I'm going to jump into runtime .h just to show you the declarations for the three things we're going to look at today. So the runtime provides, or we build managers to help manage resources that exist inside the high-level runtime. What kind of managers might we need? Well, first, if I search for class memory manager, we have a memory manager class. And the idea of this memory manager class is it's going to track the usage of specific memories. And when I say memories, I'm actually referring to the low-level runtime memories provided as part of the machine interface the low-level runtime has. So for every one of those memories, we end up creating a physical instance inside of the low-level runtime. We're going to have a memory manager to track all the physical instances that exist inside of that memory. And so we make one of these memory manager objects for every one of the low-level runtime memories that we're going to actually allocate physical instances in. One of the things we're going to see is we actually lazily instantiate these memory managers, so that we only need to create them for instances that we actually create memory, or for memories that we actually create instances in. And the reason for that is, if we're running on a really, really big machine, there might be many thousands of memories that exist across this machine. And we don't want to have, unnecessary data structures for memories that we don't even need to be tracking anyway. So we'll see how memory managers get made in just a minute. Let's just look at two of the other kinds of managers that we have here. We also have a class called message manager. And the idea of these message manager classes is to provide an endpoint for communicating with other nodes inside of the system. So you recall that we create one high-level runtime instance per node. Well, sometimes we're going to need to send messages to other nodes. And so what we do is we have these message managers, which we use to send messages to other remote nodes. And we're going to create a separate message manager for every other remote node that we're going to need to possibly send things to. And again, we're going to instantiate these message managers lazily as we need them on demand, so that we only create the ones that we need. So if we're running on a really huge cluster that has thousands of other nodes, if we don't want to have to create 16,000 or 32,000 message managers to send messages to every other node that exists inside the system, if we're only going to be communicating with, say, our nearest neighbors, the 6 nearest nodes relative to us or whatever. So we allocate these message managers lazily. We'll look a little bit more detail on that in a minute. One other cool thing that these message managers provide is they provide effectively an in-order channel for sending messages to remote nodes. So all the messages that get sent through a message manager to a remote node end up appearing on the other side in order. Doesn't necessarily mean that they have to be sent in order, but does mean that they end up getting put together back and handled on the far side in order. The low runtime, we'll see a little bit later, can actually reorder these messages and then put them back together a little bit later. And the final manager that we're probably going to look at today is the processor manager class. And the processor manager class is designed to manage all of the low runtime processors that we have on our local node. Now, in this case, we'll see that we'll eagerly instantiate these processor managers. And the reason for that is that we know we're going to actually probably want to end up running something on all of our local processors within our node. And here, because we're not actually creating processor managers for all the processors in the machine, just the ones on our local node, it's okay to eagerly instantiate all of these processor managers. And the processor managers are going to be responsible for tracking what tasks are running on which processors on the low runtime. And we're going to see that it's also going to be responsible for handling a lot of the meta work and controlling how fast and at what rate the meta work that we have to do for things like dependence analysis and mapping analysis and so forth gets scheduled onto our low-level runtime utility processors. Okay, so let's actually go and jump back and we're going to go look in runtime.cc, and we're actually going to look very briefly at a couple of these different classes. So let's start with the message manager. It's the simplest one to look at. Just to give you an example of one of the calls that might exist that causes a message or a memory manager to be. If I said message manager, I meant memory manager. We're actually going to take a look and see one of the calls that actually might cause a memory manager to be created. So if I search for create, thought it was create physical instance. I could be wrong. Let's see. We search for message manager, or sorry, memory manager. I always get these confused. I will try to be more precise. There we go, allocate physical instance. That's what we wanted. Two versions of allocate physical instance, one on the message or on the memory manager class. The other one is actually on the runtime. And this is what we'll see is a little later. There's going to be calls from the region tree data structure when we actually do physical dependence analysis that we'll need to create physical instances. And when we do that, we actually want to register that a physical instance has been made with this memory manager. So we have this call into the runtime to actually say, tell the memory manager for this memory that we've allocated a physical instance in that memory. So the first thing the runtime is going to do is it's going to call this lookup find memory call to get the memory manager, and then it's going to tell the memory manager that this new physical instance has been allocated inside of that memory. So if we search for find memory, it's a very simple call. We have a lock here just to protect our set of memory managers because this data structure is just a map from memories to memory managers. These memories are low-level memories, so they're just handles for the actual memories themselves. And then the memory managers are pointers to the memory managers. So we see if we can find our memory manager for this particular memory inside of our data structure of all memory managers. If we found it, we can return it. Otherwise, we make a new one. So this is how we lazily instantiate memory managers on demand whenever we see a request that a new physical instance has been allocated inside of a memory. And actually, you can see this is right above the call for allocate physical instance into the runtime. Okay, and then we see that once we've actually gotten our memory manager back, we call allocate physical instance on the memory manager. So we look for allocate physical instance. Our memory manager version of it. We see we get our physical manager representing our physical instance. We take a lock on our memory manager, and then what we do is we track how much of our remaining capacity we have. We check to see if it's a reduction manager, a special reduction instance. If it is, we put it in the list of reduction instances. Otherwise, we put it in the list of physical instances. And there's corresponding calls for for freeing physical instances, and so we can track how much memory we're actually using in each of these different physical memories that the low-level runtime has. One important detail about these memory managers is that they're actually representing incomplete views of the actual memory being used in these physical memories by the low-level runtime system. And the reason for that is that we're only tracking the physical instance allocations that are being done on our local node and not across all the nodes inside the machine. And so what we do is we have a partial view of all the physical instances that have been allocated inside of this memory. And so it's important to remember that this is just a partial view and maybe doesn't represent complete information, but it tends to be pretty good. And it can definitely help mappers in their decision making. So if you've looked at the mapper interface, there are query methods for checking to see how much memory has been allocated in certain memories and so forth. And that ends up going and talking to these memory managers. We'll see a little later in a much later talk that these memory managers serve another purpose, which is tracking when we can safely recycle physical instances. I'm not going to get into that today. But these memory managers allow us to track, effectively they're providing a data structure for tracking what data has been allocated inside of a specific physical memory. Okay, let's transition. Let's actually look at one of the message managers now and see how message managers get made. So let's see if we can find a call that actually ends up sending a task or sending. Yeah, let's see how we actually send a task to a remote node. Okay, so here's a runtime call. We'll end up seeing where this call gets made at a little bit later point in time. But effectively, this is a pretty simple call. We have our runtime, and we're being asked to send a task to another processor. So we've been given our processor target, which is on a remote node, where we want to send this task to. Effectively, some mapper somewhere has requested that we're going to move this task to another node, or to a processor on another node. And here's the pointer to a task object, which says the task that we want to actually send the task we actually want to send to a remote processor. There's actually a quick out here. And actually, this is cool because it actually shows how we actually look at the processor managers too. So the first thing we do is we actually check to see if this processor is on our local node or on a remote node. So if our target processor is actually in our list of processor managers, remember we eagerly instantiate this set of processor managers. So we can actually know if this target is in our local set of processors that we manage. If it is, then it's really easy. So if we finder is in our set of processor managers, we can immediately just add this to the ready queue. We'll look at this call, this add to ready queue call, in detail in a little bit later today. But if it is, we can just immediately add it to that processor manager's ready queue. So finder error second is a processor manager from this map from processors to processor managers, and so we can just immediately add it to the queue. However, if it's not, we actually need to send a message to a remote node, which is actually going to, package up the task, unpackage the task on the remote node, and then add it to that processor's memory queue. So what you'll see is that the first thing we want to do is we want to get the message manager for the target processor where we want to send this this message to. So if we search for find messenger, we'll see that we have a very simple map here, which is actually going to, look up, well, so I should be precise. There are two variations here of find messenger. It's important to realize that there are two versions of it. So the first one is, this one that's based on target processor. And in this case, we actually need to look up what we think of as the address space ID. This is effectively the equivalent of a node ID inside of the high-level runtime for actually finding a messenger, a message manager. This find address space call, you can see it right here, is effectively a way to look up an address space based on a target processor. This is actually based around a map that we build at startup time, which actually tracks all the processors and how they're mapped to different address spaces. And so we can actually do this. This lookup is read-only. This map effectively after initialization doesn't change, and so we don't need to have a lock here to actually be able to read this data structure. And once we get back the address space, we can call find messenger with an address space to actually be able to find the messenger that we need to send our message to. Okay, and so once we've got our address space where we're actually going to send this this message, we can then go ahead and look up our message manager that we're going to use for this particular address space in this method right here. And we get back our message manager that we're going to use to send to this remote node. Okay, so let's jump back to send task. All right, so once we've got our message manager, we're going to do a little bit of work to package up our task. I'm not going to dig into this too much detail today, but effectively we create a little serializer object, which is a way of serializing an object into a buffer. We're going to do some calls that are going to end up packaging up our task. Effectively, this pack task where we pack in the serializer and tell it where we're sending it to is important. That's where we actually package up the task. And once we're done with that, we're actually going to tell our message manager to send this task to a remote node. So if we continue searching for a send task here, we're actually going to find this message manager call for send task. And you see it's a very simple task, actually, or a simple function. It actually ends up invoking a subroutine inside the message manager for actually sending tasks. So we pass in our serializer, which contains our buffer of data that we want to send. We give it the name or the kind of message we want to send, and we say whether or not we want to flush this message, which involves eagerly pushing the message out to the remote node. So if we look at package message, search down here for package message. You can see we have a very generic messer interface here for sending messages. All we get are a buffer, the kind of message to send, and whether or not it should be flushed immediately, or whether it's not okay to temporarily buffer up the message. And there's a bunch of code here, but it's really very simple. It's really just packing this message into a buffer. The message managers have a fixed size buffer. It's actually can be configured by the in the Legion config.h. There's a parameter there that says how big this buffer is. It's usually going to be around 8 or 16 kilobytes. And the reason for this is we want to send reasonably large messages. So if we can pack a bunch of smaller messages into the buffer, if this flush message is false, we can package a whole bunch of little messages into this buffer and then send them as one larger buffer. But at the same time, we probably don't want to wait for our message to get too big. We don't want to be sending huge active messages with a low runtime. And so what we can do is we can chunk any messages that are bigger than that 8 or 16 kilobytes or whatever we've set the buffer size to. We can actually split those up into smaller messages of 8 or 16 kilobytes that end up getting sent to the remote node. And so all this logic that's going on here is effectively trying to pack this buffer as full as it can, and then sending packed buffers. And if our messages are too big, we're splitting them apart into smaller messages. And the way we actually end up sending messages, if you want to actually see the send message code, you can see right here is the send message call. So if we actually need to send the message, you can see that I think it actually occurs 2 places here. There's the send message call in this case, and the send message call here if we need to actually flush, even if we're in an incomplete buffer. And what we do is we package up our message and we launch a low-level runtime task on a remote node that actually ends up running this task, or moving the data in the form of the args, which are the sending buffer and the sending buffer size, over to the remote node and running this task on a processor, which is most likely a utility process on the remote node. And so what will happen is the low runtime will actually end up doing an active message to send all this data to the remote node and then running this task over there. Notice that we get back an event that says that will trigger when this message has actually been handled. And what we do is we actually end up chaining these. If we send multiple messages to the same remote node, we end up chaining these messages together using low-level runtime events. So what we do is we keep track of the last message event from the last message that we sent, and that becomes the precondition for this task, for this message to be handled. And then we take the next event that we get back and we set that to be the last event message. So the next person that tries to send a message through here actually ends up sending a message that's chained onto the end of the one before. So that's what guarantees that our messages actually end up getting sent and handled in order. Now, low runtime is actually free to move these send active messages in different orders, as long as when they get received on the far side, the tasks are actually run in the order contingent upon the event dependencies we've actually set. So ideally, the low runtime is actually sending multiple messages at the same time, if possible, and getting some parallels in there. And actually, if possible, the network can deal with messages coming out of order. The low runtime will reassemble them on the remote side and make sure that our tasks run in the order that we sent them. So the message manager class, there's some complicated logic in here really for just managing this buffer correctly. But the nice thing is that it's really abstract, which means that pretty much anytime you want to send a message to a remote node, you just create a new kind of message. And you can see there's a whole bunch of different kinds of messages that we send to this message manager. I'm scrolling here through past all the different ones. But everywhere you see one of these package message calls with a different kind, there's a different kind of message that we send between the different nodes inside of the Legion runtime. But they all go through this interface. The message managers handle all the movement. And the cool thing is that you can have this nice interface of sending lots of little tiny messages. And this message manager will try to aggregate them up and package them all together for you into bulk messages as best it can based on the constraints that you put on in terms of whether or not messages need to be sent immediately if you set flush to true, or whether you set flush to false, in which case it might try to defer it and package up a bunch of tiny messages. And we'll see is when we actually go to move stuff like the region tree data structure around, this will be really useful. There are lots of tiny little messages, and it's nice to have an interface where we can just send lots of little messages and know that this message manager is going to aggregate them all together into bulk messages for us. Okay, before I move on to process managers, does anyone have any questions about memory managers or message managers? All right, that's good. These are pretty simple classes. They're designed to provide just generic runtime services for doing things like tracking how much memory is being used or sending messages. And the idea is that you should be able to build things on top of them and use them so you don't have to write your own custom stuff for sending and receiving messages all the time for for all the different things you need to do to communicate between nodes inside the Legion runtime. Okay, so let's actually jump now to talk about processor managers. So processor managers are the most complex version of any one of these managers. They actually have the most going on, and we'll see there's a good reason for that. Let's start by finding where these processor managers are created. So I'm going to search for new processor manager. Here we go. Okay, so here's the call where we create our processor managers, and if we scroll up here a little bit, we'll see that this is occurring inside of the runtime constructor. You recall from our very first lecture that this runtime constructor is invoked as part of the startup of the runtime. And what we'll see is if we go down here to where new processor manager is being called, we see that this is in a loop. And what we're doing is we're iterating over all of the local processors that we determined we have on our local node. So these are all the CPU and GPU processors and any other kind of processors the local runtime has told us that we have on this local node, excluding the utility processors, so not including the utility processors that we're going to use for actual runtime management. So for each of the application processors, CPUs and GPUs, we're going to make one of these processor managers to actually be able to manage the execution of tasks on that processor and track effectively all the things that are going on that processor. You see, when we create a processor manager, we give it the low-level runtime processor handle. We give it its kind of processor. We give it a pointer to this runtime that's managing it. We're going to see what the superscalar width is in a minute. We tell it how many mapper slots there are, which is effectively how many initial mapper locations there are going to be. We tell it a bunch of stuff about stealing and how many processors there are and so forth. And then what we do is we save this processor manager that we've created inside of our proc manager's data structure. This is just a map from processor handles, which is what this iterator here is pointing to pointers to processor managers. And remember again that we create this map eagerly, which allows us to actually be able to make sure that everything has been instantiated at this initialization time. And then we're going to not have to worry about mutating it again throughout the run of an actual Legion runtime. Okay, so let's actually go look at this processor manager class. Let's actually jump back here. We'll see a little bit. We're going to go into runtime.h and actually look at processor manager. Okay, so if we search for processor manager in here, we're going to see there's some indication here. These structs that you see are these different kind of arguments, deferred high-level runtime metatasks that our processor manager is going to want to watch. This is how we package our args. Remember, anytime you see this HLR task ID, that's effectively a precursor for saying what high-level runtime metatask we're going to want to run. Some of these, which should give you a hint that this processor manager is going to be deferring a bunch of work onto our utility processors. Okay, so what we're going to see is that our processor manager, one of the first things it's going to be responsible for doing is actually tracking all of the mappers that exist for a given low-level runtime processor. So we have a little interface here for managing the sets of mappers that are associated with our particular processor that this processor manager is managing. And so if you recall from the Legion programming model, one of the things that we do is we provide a mapper interface, which allows you to change how tasks are going to be run. And in particular, what we do is we create a separate mapper for every single one, for every kind of mapper. We create a separate mapper for every low-level runtime application level processor. And so what we see here is that actually it's the responsibility of the processor manager to manage all the different kinds of mappers that exist for a given low-level runtime processor. So all the calls for adding and removing mappers or replacing the default mapper all ultimately end up getting translated to one of these processor managers for each of the low-level runtime operations. So when you register new mappers via the Legion interface, what we end up doing is we end up turning around and finding the right processor manager and telling it to, either add a new mapper at a particular mapper ID in the case of this first call. So here we're given a new mapper ID and a new mapper, and we say, add this to our set of mappers for this processor. There's a little check flag here just to check to make sure we're not overwriting an existing mapper. There's a replace default mapper call. So if we're given a new mapper and we want to replace the existing default mapper, we can actually do that. And there's a way to find the current mapper given a mapper ID for this particular low-level processor being managed by this processor manager. So if we actually scroll down here, we'll actually see that what we have here is we have a vector of mapper objects, and it's our job to track, keep track that all of the keep track of all the different mappers. Actually, mapper ID is used to index into this vector of mappers. One important detail that you'll see is that one of the things that this processor manager also does is it keeps track of a set of reservations for each of these different mapper objects. And the reason for this is that we actually don't want to have programmers reason about mapper calls being thread safe. So what we want to do is make sure that all calls that go into any one of these mapper objects that we're tracking is actually serialized, so that programmers don't need to write mappers with locks and so forth, which would be kind of nasty. And so what we do is we actually keep a separate vector that mirrors this mapper object. It'll always be the exact same size as this. This mapper locks vector will always be the same size as this mapper objects vector. And it'll have a reservation that we use for actually serializing access to the mapper objects. So every time we do a mapper call, we'll make sure we acquire that lock first and then do the mapper call so that we know that mappers actually have the illusion of being serialized and only getting a single call at a time, so they don't need to be thread safe. Because it is possible for the high-level runtime to generate multiple mapper calls from different utility processors that all want to know the same thing from the same mapper object. So we're using these reservations to serialize stuff. Okay, so coming back up here, after we've set up our mappers that exist for this processor, what we actually do is we actually have a whole bunch of calls here. I have a common idiom here, which is we get requests to actually invoke the mapper to do certain mapper calls that our application might need to do in order to actually map tasks and map regions and so forth. And so every one of the mapper calls in the mapper interface has a corresponding call here in the processor manager, which asks us to actually invoke that mapper call on our particular mapper for this processor. And so what you see is we have invoke, set task options, select variant, premap, map task, and we get passed in all the arguments that we're going to end up passing to those mapper calls. And so this is just the interface by which we can actually go about invoking these different mapper calls on the mapper objects that our processor manager is actually managing. One cool thing you'll see is that there are actually variants of these on the actual high-level runtime itself, and it's responsible for actually dispatching to the particular mapper processor manager. So for example, if we look for invoke mapper set task options, one here in the processor manager, but I guess let's see if I can actually type here. Let's see if we can find the one in the actual high-level runtime. Maybe I'm missing it. See if I gave it some strange name. Let's see. We'll do it the hard way. Searching through the list of high-level runtime calls here to make sure that we see if we can find the call that actually asks us to look up the processor manager and then do the associated mapper call. Here we go. Oh, that's the reason I couldn't find it. So here it just doesn't have one for set task, and there's a reason for that, is that we actually don't need it. But you see, these are corresponding mapper calls. So if you'll notice, let me actually show this to you for a different mapper call. So if we look for invoke mapper map task, very simple one. We actually see there are two versions of this one. There's one inside of the runtime class. So if I scroll all the way up here, this is the runtime class. Here we go, class runtime. It's the one inside the runtime class. And this one is going to be responsible for actually finding the right processor manager and then invoke based on the settings of this task operation. And then what it'll do is actually go and look up the right processor manager to actually run this mapper call and then turn around and call the corresponding method on a processor manager. And so we're back here. Actually, I guess here we are, back here in the processor manager. Maybe not. Maybe I went too far. Here we are, back here in the processor manager class to actually invoke the right method on the mapper for a particular low-level runtime processor. Okay, so we have a whole bunch of mapper calls here that we're supporting. We get all their arguments for passing them through to the mapper calls. We'll actually probably go look at one of these in a minute, just to give you a feel for how this mapper call looks, what it actually looks like for one of these. But let's actually look at some of the other things that our processor manager is going to be expected to do here while we're here in the runtime.h class. So one of the other things, so the other important things that message managers are responsible for, or processor managers are responsible for doing, is actually managing the scheduling of all the operations that are running on this low runtime processor onto associated utility processors and so forth. So if we're doing dependence analysis or mapping analysis or anything like that, it's up to this processor manager to make sure that those things happen at good rates and at the right point in time. So you remember when we actually started looking at the operation class, we saw cases where we saw calls like let's see, add to dependence queue, add to ready queue, and add to local queue. You can see these three calls here are declared on this processor manager interface. And the reason that we're bouncing all these operations that are going through the operational pipeline off of this processor manager is that we're allowing the processor manager to effectively rate control how fast and when these different operations are being scheduled onto low-level runtime resources. So by bouncing, the operational pipeline off of these processor managers, we're giving them some control over how fast things are progressing through the pipeline. Obviously, we could have just made the operational queue just continue, churning along and not bouncing off the processor manager. But it would have just there would have been no way to rate control how fast things were getting scheduled onto the low runtime. So effectively, these three calls here are how we control how fast things get mapped onto the low-level runtime. And what we'll see is that we also have some calls here. They're actually going to be called by probably these two are the most important. Are actually going to be called, effectively are callbacks from actual meta tasks that we launch onto utility processors that control when we're actually going to do scheduling for various operations and tasks. And so we're going to look at perform scheduling and launch task scheduler just to see what else is going on. Other things that are going on here. There's also processor managers are also responsible for managing information about stealing and so forth, and that's not surprising because they're actually managing the mappers for a particular low-level runtime processor. And we probably won't get into stealing today, but you can just be aware that these are some of the other responsibilities that the processor manager has to deal with. Let's see, we'll probably end up looking at some of these other calls, like performing mapping operations to see how we actually look at mapping tasks onto low runtime. I guess most of these other data structures we're going to come across here as part of our discussion. So you can just be aware that they are here, all declared in the processor manager class in runtime.h. Okay, so I'm going to jump back. Let's go back to runtime.cc. We'll actually look at some of the code for these processor managers. Okay, so I'm searching for processor manager. Okay, here's our queue. Here's our constructor. You see what we do is we allocate a whole bunch of locks and other resources that we need. One of the important things that we do is notice we actually create a vector of default mappers of the right size based on how many initial default mappers we want to have. We initialize all the pointers to null, but we can actually fill those in later. Same thing with our reservations for our mapper locks to make sure that we have the right number of those. Let's see, we have a bunch of calls here. If we actually look here, here's an example of how we add a mapper. You can see that for every new mapper ID, we get a new mapper and we get a check. If we're actually going to do the check, we're going to check to see if we've already have a mapper ID of a certain kind to see if we've picked a bad value. In this case, mapper ID 0 is usually reserved for the default mapper. You can, of course, override that by using replace default mapper. You can see if our mapper ID is bigger than our initial number of mapper objects, we can resize all our things and then insert the fields that we need to. And every time we create a new mapper, we also create a new corresponding reservation, which I'm highlighting here, that's going to be responsible for serializing access to this mapper. We get a call to replace default mapper, which does something similar. There's a call to find mapper and so forth. Okay, let me actually walk through one of these invoke mapper calls, just so you can see what actually goes on. We'll just do this first one here, invoke set task options. There's actually a fair amount of logic that's going on here, and it looks kind of complicated, but I assure you that it's actually not. So one of the things that we allow our mapper objects to do is to actually be able to send messages inside of any mapper call. And another thing we allow them to do is inside of any mapper call, they're actually allowed to defer mapper operations to a future point in time. So what we want to do is actually set up some metadata structures that are actually going to be used to track whether or not we've actually gotten any of these message calls, and also to track whether or not we've actually deferred our mapper call to a future point in time. So that's what these two data structures here are going to do. We set up a little do while loop, and the idea here is that if we do get a wait for our mapper call, we actually want to be able to defer that mapper call to a future point in time. And so what we want to do is be able to actually wait on a low runtime event in case the mapper asks us to wait for a certain condition to become true before our mapper returns. We'll actually look at that in just a minute. But this first time through this loop, what we'll see is that if we had a previous defer event, we're going to be asked to wait on it. If that's the case, most likely this wait on event is going to be a no event. As Sean mentioned last time, we have no events, which correspond to events that have already triggered from the beginning of time. So most likely this wait on event is a no event. So we're going to skip this if wait on exists. We know that we have a no event, so we're not going to wait on anything to start. Once we do, before we can actually do the mapper call, here's where we take our lock on our particular mapper before we actually do the mapper call. And this allows us to serialize all the mapper calls so that we don't have to have our mappers be thread safe. We have a little data structure here that tracks whether or not we're inside of a mapper call. Notice all of these data structures are being indexed by the mapper ID this particular task operation is working on. So we're all working on the same mapper ID local to this processor. We then actually end up doing the mapper call. So for those of you that are familiar with the mapper interface, this is the actual mapper call that goes out to the mapper object. So select task options is a virtual method on a mapper object, and it actually performs the actual mapper call. So once we've popped out of we do that call, and then when we pop back out, we say that we've mapped, we're no longer inside of a mapper call. One of the first things we do is we check to see if during the mapper call, while we were running select task options, the mapper actually requested that we actually defer this operation for a future point in time. If it did, what we end up doing is actually end up that call will have put a new low runtime event onto this defer mapper event that tells us when we want to actually wait for this mapper call to finish. We actually end up marking that as our new wait on event. And if we did get one of those, we've recorded it, so we can then set this event back to a no event. And then we do continue. So that's in that's why we're in this do while loop. When we jump back around, we're going to end up seeing that wait on is now we want to wait on, so we block waiting on it. And when I say block, we actually set block to false, which allows the low runtime to reclaim this processor that we're running on and actually use it for doing additional work. And at some point later, that event will trigger and we'll wake back up here and we'll be able to actually invoke the mapper call again in case the mapper wanted us to run at a future point in time. Now, if we did succeed, if the mapper didn't ask us to defer it, another thing that can have happened was that the mapper actually asked us to send some messages as part of its execution. So sometimes mappers are allowed to send asynchronous messages either to another mapper of the same kind at another processor, or they can ask to broadcast messages to all the other mappers of their same kind in the system. And so what we do is we take a little lock here just to check to see if we've actually been requested to send any messages for this particular mapper ID. If we were, then we pop them off of this data structure, this mapper messages data structure, which got filled up as part of the during the call to this mapper call that we were running. So we copy that into this local set of messages that we are pulling off here on our stack. We can then clear those messages since we pulled them out of the data structure. And then once we've jumped out of this loop and we've released all of our locks, then we can actually go and actually send any messages the mapper asked us to send. The reason we need to do it this way, the reason we can't just send the messages while we're inside of the mapper call, is that we're actually holding this mapper lock. And it's possible that those messages could actually get sent to another mapper in the machine, which handles those messages and then turns around and sends a message back to us. And what we can end up doing is that can all happen inside of one thread, which ends up causing deadlocks. So we have to defer our message sends until we release this mapper lock in order to be safely avoid deadlock in all cases. So that's why we effectively defer our message sends into this data structure, this mapper messages, and then we send it after we've actually released the mapper lock that we were holding when we were doing this mapper call. And what you'll see is that this format of how we invoke mapper calls in terms of buffering messages and checking for deferred mapper calls is mirrored across pretty much every single one of these mapper calls that we're going to do. Unfortunately, it's kind of hard to abstract all the details for doing one of these mapper calls. We could do it with macros, it'd be kind of ugly. But effectively, all of these processor manager calls to invoke a mapper have the same structure that I just described. So they all look kind of scary, but really they're all the exact same piece of code, just doing different mapper calls. So here's notify failed mapping, and here's notify mapping result, and so forth. But really, they're all just wrappers on this same call to actually invoke mapper calls. Okay, so I have about 15 minutes left, and what I want to do is actually jump now into some of the scheduler calls that actually get done that we've seen from the operational pipeline, just to tie some things back together. So I'm going to keep searching for processor manager, and I'm going to search for perform dependence analysis. I think it's the right one, or maybe it's let's see here. Should be right down here somewhere. There's process steal request, advertisement. Here we go, add to dependency. This is the one that I wanted. Okay, so if you remember, in our operational pipeline, one of the first things our operations do is once they've registered them, initialized themselves, they say to add themselves to a dependence queue. And so here's where we get past our operation, our generic operation that gets passed into add to dependence queue. And what you'll see is it's the job of the processor manager to figure out, we want to put this dependence queue operation onto a low-level runtime utility processor to actually perform this analysis. But we need to do it very carefully. We want to make sure that all of the dependence analysis for operations within the same context end up going to the same, or end up being done. Remember, we need to do those in order to be correct. So one of the things that we do, the first thing we do is we're going to do one of these high-level runtime meta tasks. We're going to launch one of these off on a utility processor so that we can get us some deferred execution and have it run at a later point in time on a utility processor. So we build up one of these deferred trigger args structures. And again, here you can see we're filling in the task ID for a high-level runtime meta task. And in this case, it's the trigger dependence ID. And we're filling in our manager, which is ourself, and the operation that we want to trigger when we do this call. And the next thing we do is we actually get the context ID for the context this operation is executing. Notice that we get the parent task. So this op arrow get parent task is returning one of those single task pointers that points to the parent task for this operation that we have on our local node. Then we're asking for the context ID. And effectively, this is a unique identifier which we can use to represent this parent, the context in which this parent task is, or the context represents this parent task. And really, this context ID is just an unsigned integer that we have for representing an available context on this local node. So what we're going to do is we actually want to make sure that all the operations inside of this context have their dependence analysis performed in order. So what the processor manager does is it maintains a data structure called dependence preconditions that maps these context IDs to low-level runtime events. And what the low-level runtime events represent are when the dependence analysis from the previous operation in this context has completed. So what you can see that we're going to do here is we're going to launch this, our dependence analysis for this operation. We're going to spawn this onto a low-level runtime utility processor. We give it the high-level runtime meta task ID, and we give it our set of args that we've packaged up here to send. And we're going to defer this operation and say that it can only run after the event has trigger the previous operation's dependence analysis within this same context. And so the idea here is we actually want to make sure that dependence analysis is happening in serial for operations from the same context, but they can actually be happening in parallel from operations for a different context. So this dependence preconditions tracks the previous event, or the event precondition the event that represents the termination of the dependence analysis from the previous operation in this context. And so that's how we defer our task and make sure that dependence analysis is done in order for all the operations within inside of a context. And then you see what we could do is we get back an event next, which represents when we're going to be done with our dependence analysis that we just launched. And then we put that back onto this set of preconditions for this particular context, saying that we're not allowed to actually run our next dependence analysis until this next event has triggered. And notice we do all of this while holding this dependence lock, which makes sure that this operation of launching this task and then updating this data structure occurs atomically. This allows us to guarantee that we get the right semantics for all these operations. And one of the important details here is there's actually no rate limiting on this dependence queue operation. And the reason for this is that there's really no need to actually limit these. We can keep queuing them up and launching them in a little runtime. We're not going to have any starvation issues because we know we are only going to be executing these operations in serial within a side of a single context. And so there's really not that many contexts floating around, and so we don't have that many operations that can, that are ready to run on the low runtime at a time. Okay, so that's add to dependence queue, which was a call that we had seen earlier, but I hadn't really explained in much detail. But now you can see how the processor managers actually help facilitate that operation onto a particular utility processor. I'll mention briefly that this utility processor is actually passed in from the high-level runtime when we create this processor manager. So if I scroll up here, if we actually look for the processor manager constructor, one of the things we'll see, or actually I think we set it here inside of the, here we go. We set this utility processor when we actually construct the processor manager, and it stays the same throughout the lifetime of the processor manager. And what you see is this utility processor is finding what we call the utility group for the high-level runtime on this node. And this utility group is really just a queue which feeds into all of the low-level runtime utility processors on this local node. And the high-level runtime is responsible for making this. It's a very simple operation that just tells the low runtime, group all these utility processors together and make a common queue that you'll load balance from. And then we just use this utility group handle to actually name this queue. And we use it pretty much everywhere for deferring all of our low-level runtime operations. And so we get good load balancing of all of our meta tasks across the low-level runtime utility processors within a node. So that's what this utility proc is and where it comes from. Okay, let's jump back here to add to dependence queue. So we did add a dependence queue. Let's actually look at another one. Let's actually look to add to local ready queue next. We'll look at add to ready queue after that. So you remember that add to local ready queue is called by any of our operations that are not tasks when they were ready to actually be mapped and run. And so what we do is we're getting a generic operation here that says this is the operation we want to add to our local ready queue of things to do. And we get a little notification here just saying whether or not this operation has failed either to map or has been restarted for some reason in the future. Most likely this value is false. We haven't had any previous failures, but you never know. Okay, and so what you see, you're seeing a common pattern here. We're again going to defer this operation onto the utility processor. So we're going to build up another set of arguments here that we're going to use for launching a high-level runtime meta task. This time we're giving a different meta ID. This is going to be trigger operation ID, which is going to invoke trigger execution on this, trigger mapping on this this operation. And then we're tracking, the manager, which is this, and the operation that we're actually launching. You'll see a couple of different. The common case here is this not previous failure case. What you'll see is that in the not previous failure case, what we're going to do is we're actually going to take a lock on our local queue. So this is our local queue for operations that need to be scheduled onto this particular processor. What we're going to do is we're going to launch the task onto our utility processor, asking it to actually perform the mapping for this operation. Now, one of the challenging parts of this process is that we actually have a way to, we can actually, if we're not careful, we can end up flooding this utility processor with a whole bunch of requests to do mappings and other meta-analyses. And so what we do is we want to kind of throttle the rate at which these operations progress through the low-level runtime so that they don't get in each other's way and cause starvation for other operations that might have, higher importance that come a little later. So what we do is we keep effectively a little vector, and it's this local scheduler preconditions that effectively has different chains of low-level operations that we've launched onto this utility processor for this particular processor manager. And so what we do is we're actually going to pull an event off of this local scheduler preconditions. Effectively, what we're going to do is we're going to round robin things onto these different chains of low-level runtime operations, so that we have these chains and it'll help throttle the rate at which the low-level runtime has stuff to do. And what we do is the size of this vector is actually controlled by a parameter which you can set in the config for the Legion runtime. Let me just actually show you where it comes in here to the processor manager constructor. You can trace it back yourself. One of the things that we get is this unsigned width, and you'll see that the high-level runtime likes to refer to this as the superscalar width, and it's drawing on the analogy of the high-level runtime as an out-of-order superscalar processor. And effectively, this width says how many of these parallel operations, chains of low runtime operations we can have going in flight at a time. And so you can control how much parallelism you expose to the low runtime at the cost of possibly, overloading the low runtime. Usually this width is about, 4 or 8 or something very small. So that's controlling how wide this local scheduler preconditions is. And so what you can see is we pull an event precondition off of this local scheduler preconditions corresponding to some index. And then after we're done actually doing this, what we do is we increment our index, and if our index is grown to our superscalar width, then we set it back to 0. So we just keep round robbing operations onto these different chains of low-level operations. And really, we're just adding artificial dependencies here. There's nothing about correctness here to control how fast these operations are actually running by the low runtime. We just want to make sure that there's not a million of them all ready to be triggered on the low runtime at a time, and have a way to actually control so that in case we have important operations that come later, that we actually want to sort of mix in and keep moving. And so that's really all this local scheduler preconditions is doing. It's just tracking events and keeping chains of events. And once we've gotten our event for our next operation, we append it, or we set it to be the next value, and then we increment our local index, and we check to make sure we don't overflow and so forth. And notice again, this is done with this local queue lock, which makes sure that all of these operations are done atomically. Now, in the case where this is the case where we didn't have a previous failure, but in the case where we did have a previous failure, notice we just turn around and immediately launch the operation onto the low runtime immediately just to get it going, because it's likely that if we've failed before, we actually wanted to get it running again pretty soon, because it's likely blocking other operations that are waiting to run. Okay, so let's add the local queue, which handles all of our other operations. I'm almost out of time for today, so what we're going to do is I'm actually going to postpone the discussion of what add to ready queue does and how we actually manage the ready queue for tasks to next time. We're going to see a little bit next time about how the scheduler actually works for scheduling some of these tasks onto processors. The scheduling of tasks is a little more complex. There's a lot more things that have to go on in order to get them through these processor managers. So we'll look at that in more detail next time. And with that, does anyone have any questions before we finish for today? Nope. Okay, great. I think I will be back on Wednesday to talk about processor managers, and specifically about how we schedule tasks and how they progress through these processor managers. And with that, anybody has any questions, feel free to email us on the discussion list. All right, thanks.